This is the first video in the mole unit. You can see the learning targets here for this video. We have 4 learning targets. We want to explain how the mole is a counting number. We want to state Avogadro's number and explain the standard by which it is determined. We want to identify the representative particles in a sample of matter. And finally, we want to use Avogadro's number to convert between moles and particles of a substance. First of all, some key ideas. The mole, and we've probably already discussed this in class, the mole is a counting unit. It's a counting unit. Like dozen. We know that there are 12 items in a dozen, or a pair, or a gross. These would all be examples of counting units. The mole is also a counting unit. A difference, I'll zoom in here a little bit. The difference is between the mole and these other things we're familiar with. The mole is way, 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 way larger. Okay, it is much larger. 1 mole of anything is equal to 6.022 times 10 to the 23rd. Okay, that's just like if 1 dozen is equal to 12. The mole is equal to 6.022 times 10 to the 23rd. It is a huge number. It is a huge number. This is known as Avogadro's number. It is named after a 19th century scientist by the name of Avogadro. He was the first to theorize about the need for a number like this. And if you ask yourself, why is a number so big? It's because we use the mole to count really, really tiny things like atoms or molecules or electrons. And this Avogadro guy, he was the first to think, hey, we need a counting number that would allow us to count these really, really tiny things because we know there's so many of them. The standard by which the mole is determined, because as we know there has to be a standard for any measurement in science, the standard by which we know a mole is this number, it is the number of atoms in exactly 12 grams of carbon-12. So if we have a carbon-12 isotope, we have exactly 12 grams. This is the number of atoms, 6.022 times 10 to the 23rd. That's the number of atoms in that sample. That is our definition. Now when we talk about the mole and we talk about the number of things that there are, obviously we're applying this to really, really tiny things. And more specifically, we wouldn't just say a mole is 6 times 10 to the 23rd of anything, because we wouldn't apply the mole to most anything. More specifically, we would say that 1 mole is equal to 6.022 times 10 to the 23rd representative particles. And I'll explain what that means here. If we have an element, like for example, well, let's just go with copper. If I have a sample of copper, so here's my copper sample, what I'm going to have in here is I'm going to have a whole bunch of individual copper atoms. I'm just drawing circles to represent copper atoms. So if I have 1 mole of copper, 1 mole of copper, and recall that the symbol for the mole is MOL, that would equal to 6.022 times 10 to the 23rd copper atoms. If we have a molecular compound, or what we might call a covalent compound, and a key to identifying molecular compounds is it's made of nonmetals. Like for example, water. If I had a sample of water, let's draw another picture here. Okay, we know from the formula that the formula for water is H2O. What that tells us then, in 1 molecule of water, there would be 2 hydrogen atoms, and 1 oxygen atom. So what I'm drawing here is just representing water molecules. And that's exactly what we would call a mole of water then. We'd say 1 mole of water equals 6.022 times 10 to the 23rd water molecules. Not atoms, because we talk about a mole of water, we're talking about the whole thing. Okay, a unit of water is the molecule. Alright, lastly, if we have an ionic compound, this would be like sodium chloride, then when we talk about a mole of sodium chloride or any other ionic compound, we have to consider that these ionic compounds form crystals, and this is something we've talked about in class a little bit. Remember, these ionic compounds form these repeating patterns of ions going over and over and over. Now, I'm not showing the charges here. Suppose I could put pluses and minuses in these, that would make sense, where the pluses are the sodiums and the minuses are the chlorines. When we talk about an ionic compound, there is no single unit like we have over here with a molecule or an atom. When we talk about an ionic compound and a mole of it, we just take one unit of the formula. Notice the formula for sodium chloride is NaCl. So a formula unit is one sodium ion and one chloride ion. So a mole of sodium chloride, NaCl, is equal to 6.022 times 10 to the 23rd NaCl formula units. So if I had a mole of sodium chloride, I would have 6.022 times 10 to the 23rd of those units right there that I put in the small box. In other words, one sodium ion and one chloride ion. Alright, so let's look at how we can use Avogadro's number in a problem. Notice all these equalities we wrote up here. They are in fact equalities. 1 mole is always equal to Avogadro's number of particles, whether it be atoms, molecules, or formula units. So I can always use that as a conversion factor. So I look down here at practice problems. I can see here I'm asked determine the number of particles in 0.65 moles of copper. So I'm finding the number of particles. Well, the particles in copper, and it's the same example I used up here, would be atoms. So how many atoms are equal to 0.65 moles of copper? Well, I just asked myself, how many atoms of copper are in a mole of copper? Well, I know that 1 mole of copper, and that needs to go on the bottom so the units cancel, would be Avogadro's number, or 6.022 times 10 to the 23rd atoms of copper. That would be the particle, the representative particle of copper. Okay. And notice here I would get 2 Sig Figs because the 0.65 is just 2 Sig Figs. And I believe that's going to give you 3.9 times 10 to the 23rd atoms of copper. Alright, number 2. Very similar. How many particles are in 8.78 moles of water? Why don't you pause the video and try to do this yourself. Alright, so what we can see here is the same question as above. We're trying to find the number of particles, but this time we're asked about particles of water. Well, if we look back up at our example here, the smallest particle, the representative particle of water, would be called a molecule. So how many molecules of water are equal to 8.78 moles of water? Well, same conversion factor as before. I know that 1 mole of water would be equal to Avogadro's number, 6.022 times 10 to the 23rd, and this time I'm going to label it molecules. If you're looking for an abbreviation for molecules, I would use just CULES, cules. I wouldn't use MOL or MOLE because that would mean mole or say mole, so I would not use those because then you're going to get yourself confused. And the same calculation as above. Okay, the number of moles times Avogadro's number. I believe this is going to give you 5.29 times 10 to the 24th molecules of water. Okay, number 3. Again, go ahead and read this question and try to do it on your own. We're asked to determine the number of particles in 0.0028 moles of lithium bromide. Well, so it's the same question as before. How many particles? Well, this time the particle, lithium bromide, would be ionic. I know that because lithium's a metal and that would make it ionic. It's going to be formula units. So how many formula units are equal to 0.0028 moles of lithium bromide, LiBr. Same calculation as before. I'm going to put Avogadro's number on top, 6.022 times 10 to the 23rd. Formula units, LiBr, and 1 mole, LiBr on bottom. Moles cancel. And this would give us 1.7 times 10 to the 21st formula units, LiBr. Alright, number 4 is the reverse of what we have been doing. A sample of oxygen gas contains 9.0 times 10 to the 22nd molecules. How many moles of molecules are in this sample? So here we're given a number of particles, and we're asked to find how many moles. So, question mark, how many moles of oxygen? Now notice, it says oxygen, but it says we have a molecule. You might think, well, why wouldn't it be an atom? Well, that's because oxygen is a diatomic element, meaning it does not normally exist as an individual atom. It exists as two atoms, thus diatomic. Two atoms of the same element bonded together. So that's why we use the term molecules instead of atoms. So how many moles of O2 would be equal to 9.0 times 10 to the 22nd molecules of O2? So notice now we're starting with the particles. So in our conversion factor, we need the number of particles. That would be Avogadro's number, 6.022 times 10 to the 23rd molecules of O2 in every mole of O2. Molecules cancel. We're left with moles, and we're done there. And this should give us 0.15. 0.15 moles of O2. Alright, next one. How many moles of carbon are in 4.05 times 10 to the 25th carbon atoms? If you compare it to what we just did, you can see it's the same thing. We're asked to find the number of moles. How many moles of carbon are equal to 4.05 times 10 to the 25th atoms of carbon. So here we're going from particles to moles, so it's the same conversion as before. We know that 1 mole of carbon, not copper, carbon, would equal 6.022 times 10 to the 23rd atoms of carbon. And this gives you 67.3 moles of carbon. Alright, last two. How many oxygen atoms, so question mark, atoms of oxygen are equal to, or are in, 2.50 moles of carbon dioxide? So notice here, we're talking about two different substances. I'm starting with moles of carbon dioxide and need to find atoms of carbon. Our first conversion factor will be using Avogadro's number. In 1 mole of CO2, there would be Avogadro's number, 6.022 times 10 to the 23rd. The question is, Avogadro's number of what? Well, if I have a mole of carbon dioxide, I have a mole of that entire particle. So that would be molecules of CO2. Okay, not atoms of oxygen. Okay, just because I'm looking for atoms of oxygen doesn't mean I can put atoms of oxygen on top here in this unit. If I have a mole of the CO2, then I have a mole of that whole particle. So now we need to go from molecules of CO2 to atoms of oxygen. Well, we can do that simply by looking at the formula. I can see that 1 molecule of CO2 has 2 atoms of oxygen. I can get that straight from the formula. I can see the subscript 2 there. That tells me in a molecule there would be 2 atoms of oxygen. So molecules of CO2 cancel, and that's what we're looking for. should give us 3.01 times 10 to the 24th atoms of oxygen. And last question. We're told a sample of sucrose, which is C12H22O11, contains 6.75 times 10 to the 24th atoms. How many moles of sucrose are in the sample? Okay, so we're asked how many moles of sucrose, so how many moles C12H22O11. That's what I'm looking for, and we're told that this sample contains 6.75 times 10 to the 24th atoms. Now it doesn't say atoms of what element, it just says atoms, so that's total then. There's total. Now notice it's important that we recognize this as atoms and not molecules. If I was talking about the smallest particle of sucrose, or the representative particle, the term would be molecules. But if it says atoms, we're talking about the individual atoms that make up the molecule. So if I'm going to go from atoms to moles of the sucrose, I need to know how many molecules this is. Well, I can just count up the number of atoms in a molecule. There are 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. 12 plus 22 would be 34, plus 11 would be 45. So there are 45 atoms in every molecule of sucrose, C12H22O11. Now I can use Avogadro's number. I know that there would be 6.022 times 10 to the 23rd molecules of C12H22O11 in every mole of sucrose, C12H22O11. Now molecules cancel, and we've done the problem. And I have not worked this one out yet, so let me plug it into my calculator. So 6.75 times 10 to the 24th divided by 45 divided by 6.022 times 10 to the 23rd. And we will get, looks like 3 Sig Figs here. This would be 0.249 moles of sucrose, C12H22O11. Note about Sig Figs here. Avogadro's number is measured, meaning as we write it, the 6.022 times 10 to the 23rd, that is 4 Sig Figs. You could look it up to more Sig Figs if you wanted to. Very rarely would we ever need more Sig Figs than that, so it's really not necessary. And notice here, this first conversion factor we use, there would be exactly 45 atoms in a molecule. You can't have part of an atom. And this would not be measured. This would simply be counted. We could look at the fact that look at the atoms in the molecule, know that there would be exactly 45. So that's not going to count against your Sig Figs. So in this problem, what we're limited by is this initial measurement of the number of atoms. So that's why we get 3 Sig Figs there.